Hi guys, welcome to chapter 11. We are jumping through chapters. I think we just did a couple sections in chapter 8. We're going to jump up to chapter 11 for our next topic, infinite series and sequences. So the first section in chapter 11 is sequences. An example of a sequence is maybe something like 1, 4, 9, 16. What we look for in a sequence is just a set of numbers in order. Order is important, and we look for some sort of pattern. So if you can think ahead, you'll probably know or guess that the next element would be 36, the next term, and we can continue like this. When we put those 3 dots, it means it continues like that forever. So there's an example of a sequence. So formally, a sequence is a list of numbers in a given order. That simple, yes. Or equivalently, a sequence, if we look at it in terms of calculus, is a function whose domain is the set of positive integers. So this would be, if our input was 1, the output would be 1. Our input is 2, the output would be 4. Our input was 3, the output is 9, so forth and so on. So each term in the sequence corresponds to an integer in order. Sometimes we can find templates or formulas for the pattern, not always, but we'll discuss that in a minute. The notation for a sequence. Get rid of that page. Okay. The notation is, well, we can do, we can list them. A1, we can use any lowercase letter, you can use any letter. We typically use lowercase letters, so A1 would represent the first term in the sequence. A2 would indicate the second term in the sequence, A3, so forth and so on forever. We can condense this notation by using our set brackets and just simply putting n as our subscript. Or if we want to be a little more precise, we can say that our values n start at 1 and they go on infinitely. So typically when we write this without the sub and the superscript right here, we're assuming that. All right, so some sequences may have a formula for finding the nth term. So let's look at the example we just did. 1, 4, 9, 16. Right. So what we typically do is we can make a table of values. My inputs are going to be the set of integers, so 1, 2, 3, 4, 5, so forth and so on. The output at the first term was 1, the second term was 4, the third term was 9, 16, so I'm just assuming the pattern continues. Okay. So here we could say that the nth term is just whatever the value of n is squared. So that would be this template for this particular sequence. This is called an explicit formula because we can explicitly find the value of any term. So if I wanted to know the 30th term, I would know I just had to square the 30th term and the output would be 900. So this is an explicit formula. Explicit means we can determine the value of the nth term explicitly just by plugging it into the template. So we would typically write this sequence like this. N squared, n starts with 1 and goes to infinity. And we'll see in some cases where n doesn't necessarily always start at 1. We'll assume it starts at 1 unless otherwise stated. So not all sequences have explicit formulas. They have patterns, but not necessarily a formula associated with them. Let's consider this. Let's suppose I gave you this sequence. 1, 1, 2, 3, 5, 8. Can you guess what would come next? Can you see a pattern yet? I'll tell you the next term is 13. Can you guess the next one? Okay, continues like this. You may or may not have seen this before. This sequence before. It actually is a very famous sequence. It has a name. So for the input 1, the output is 1. For the input 2, the output is 1. Whoops. For the input 3, the output is 2. For the input 4, the output is 3. input 5, the output is 5, 6, that's 8. All right, so in this case, this is called the Fibonacci sequence. You may have heard of this before. I'm assuming that at some point in your career you did. And each of the terms in this sequence is called a Fibonacci number. So 1, 2, 3, 5, 8, 13, 21, so forth and so on. The next one would be 34, are called Fibonacci numbers. Now, there is no explicit formula. For the Fibonacci sequence. Mathematicians have been working on this for years, like hundreds of years. So if you can come up with an explicit formula for the Fibonacci sequence, you will be very famous. We have what we call a recursive formula instead, and it's saying how I can get from one number to the next number. So to get to the third number, I have to add the two numbers before it. So 1 plus 1 is 2. To get to the next number, I add the two numbers before it. So 1 plus 2 gives me 3. 2 plus 3 gives me 5. So how we would say that is any particular term can be found by adding the term before it and adding the term, two terms before it. So if we have the nth term,